In this lecture, we're going to talk about an efficient algorithm to compute greatest common divisor. First of all, what is greatest common divisor, GCD? Greatest common divisor, if we focus on just two numbers, A and B, then the GCD, the greatest common divisor of A and B, is defined as, we use this symbol to mean is defined as the maximum number k, the maximum number, or the largest number, k, such that k is a divisor of both A and B. So basically means that k divides A, k divides B, and we want to find the largest number k, and that number is defined as the greatest common divisor of A and B. That's true for two numbers, of course. We also can define GCD for three numbers or four numbers. Basically follows the same definition, the maximum number k such that k is a divisor of all the numbers inside the GCD, this parentheses. Let's look at two examples. Example 1. What's GCD of 6 and 18? Now we know that 3 is a divisor of 6, 3 is a divisor of 18. So 3 is a common divisor, but it's not the largest. The largest is 6, because 6 is a divisor of 6. 6 is also a divisor of 18. And you cannot have any number bigger than 6, because any number bigger than 6 cannot be a divisor of 6. So GCD of 6 and 18 is 6. That is the largest common divisor of 6 and 18, and that's why it's known as the greatest common divisor of 6 and 18. Let's look at example number 2. What's GCD of 54 and 180? Again, you see that 6 is going to be a common divisor of both 54 and 180, but that is not the largest. How about, can we multiply 6 by something? Okay, how about 18? 18 is going to be a 54 equals 18 times 3, and 180 equals 18 times 10. So the GCD of 54 and 180 is going to be 18. 18 is the greatest or the largest common divisor of 54 and 180. There are several ways to calculate, to compute the GCD of two numbers. The most fundamental way is actually look like here by doing prime factorizations. But prime factorization sometimes is a bit of cumbersome, and usually is not most efficient for computer algorithm. In here, I'm going to describe a very, very simple algorithm that you can do it on a paper very efficiently. And that is called the Euclid algorithm. The Euclid algorithm is based on one simple fact. The GCD of A and B is going to be the same as the GCD of, you take those two numbers, take the larger one, let's say the larger one is A, and the smaller one is B. It's going to be the same as GCD, you subtract A from B, you get another number, A minus B, which is going to be smaller than A, and you keep the other number B. Keep the smaller number and replace the larger number A by the A minus B, subtract B from A. And you keep doing this. Every step, you pick the large number and subtract the smaller number from the large number, and you do keep the smaller number and using the difference as the second number. And you keep doing it until one number is a 0. Then the other number is going to be the GCD. Let's say you keep doing this, and in the end, you'll get GCD of the one number is 0, the other number, let's say, is k. And then the GCD of 0 and k is going to be k. Because in this case, k is going to be a divisor of 0. Don't be surprised. 0 is a multiple of everything, except that 0 is not a multiple of 0. 0 is a multiple of k, and k is a multiple of k, and the largest one, the greatest one common divisor of 0 and k is going to be k. So this is the step. Every step, you're just taking the large number, the smaller number, replace the large number by the difference of the large number and the smaller number. Let's just look at the example. Example 1. The GCD of 6 and 18. Okay, this example 1 is the same as example 1 of this. So by the Euclid algorithm, the large number is 18, the small number is 6. So we're going to replace the larger number by the difference. 6, 18 minus 6 is going to be 12. Again, we'll keep doing it. Now the larger number is 12, the small number is 6. We're going to replace this number by the difference. So it's GCD of 6 and 6. And then they are the same. The larger number is 6, the smaller number is 6. We take the difference of the large and the small and replace one number, 6 and 0. Now we stop. When GCD there's a 0, the GCD of 0, 6 equals 6. So we get GCD of 6, 18 equals 6. Okay, of course, that example is a bit trivial. Let's look at the second example of GCD 54 and 180. First step, 180 is a large number, 54 is a smaller number. So we're going to replace the large number by the difference. So GCD of 54, 180 minus 54 equals 126. Okay, this is the large number, this is a smaller number. Keep the smaller number, replace the larger number by the difference, 54 and 72. Again, GCD of 72 is a large number, replaced by the difference, 54, 18. Now 54 becomes a large number, replaced by the difference. So 36, 18. GCD of 18, 18. You see it's this is near the end. GCD of 0, 18, and you stop. This one equals 18. When you see a 0, you stop. So you see this algorithm succeeds very easily. Every step is just on paper. You take the difference, replace the large number by the difference. And this is known as the Euclidean algorithm to compute a GCD of two numbers. Now, this is simple, but sometimes could be very tedious, especially if you see that if one number is much, much larger than the other number, and you're going to do this subtraction many, many steps. So here we have an extended or refined Euclidean algorithm. Euclid algorithm. And that is, instead of using the difference to replace the large number, we use the remainder A divides B. Remember, A is the large number, B is the smaller number. Using the remainder A divided by B to replace A. And this will result in a very, very fast algorithm. Let's again look at example 1. GCD of 6 and 18. 18 is a large number, 6 is a smaller number. So we're going to use the remainder of 16 divided by 6 to replace the large number. This equals GCD of 18 divided by 6, remainder 0. So 6, 0. Okay, here this GCD equals 6. We're done. Example 2. GCD of 54 and 180. 180 is a large number, 54 is a smaller number. So we're going to replace the large number 180 by the remainder 180 divided by 54. So this equals GCD of 54. The remainder 180 divided by 54 is going to be 3 times 54, that's 162. The remainder will be 18. Now again, using this refined algorithm, GCD of 54 and 18 is going to equal GCD of 54 divided by 18, remainder 0, and keep the smaller number, 0, 18. And this we know that it's going to be 18. It still stops when GCD is 0 and a number, non-zero number, and the GCD will be equal to that non-zero number. So you see, by this refined Euclid algorithm, to calculate GCD of two numbers becomes really fast. So in this lecture, we talked about GCD, to compute GCD for two numbers using the Euclid algorithm. In the end, I'm going to just briefly mention how to calculate GCD, let's say 3 or 4 numbers. If we calculate GCD of A, B, C, 3 numbers, we can calculate the GCD for A and B first. This one pair, and then compute the GCD of this GCD of A, B, and C. So to compute the GCD of 3 numbers, we first compute the GCD of A, B, and then we compute the GCD of that, the new number we computed, and the C, the GCD of this new number. And you see that if I want to compute the GCD of 4 numbers, you can first compute the GCD of 3 numbers, and then compute the GCD of that GCD with the 4th number. And that algorithm can be done recursively. And that's the end of this lecture.